Today we're going to talk about inverse functions. So we'll start with the definition. A function, it looks like it's f being raised to the -1 power of x, but that's not actually an exponent. That -1 represents inverse. So this is read f inverse of x is called the inverse function of f of x if and only if f composed with f inverse of x gives you x, and f inverse composed with f of x gives you x. If you recall from previous knowledge, we said when you compose two functions together, you don't always get the same thing. F composed with g gives you something completely different than g composed with f. Here's a situation that when you compose these two functions together both ways, it does in fact give you the same thing. More specifically, it gives you x. What an inverse function is, it's what undoes the original function. So think about when you learned math, you learned addition, then you learned how to undo it, so you learned how to subtract. You learned how to multiply, then you learned how to undo it, you learned how to divide. What an inverse function does is it undoes what the original function did. So remember when we said that a function, you stick an input in, does a bunch of stuff, and spits out an output. Your inverse function is going to take that output, undo everything your function did, and spit out that original input. So it turns out that the domain of f is the range of f inverse, and that the range of f is the domain of f inverse. Their domains and ranges are just switched. So the way to think about it, if you had an ordered pair a comma b on f, switch that, then b comma a would be on f inverse. What that means even further is that f and f inverses are just a reflection of one another over the x equals y or y equals x axis. So if we had this right here, here's x equals y, right here. If we folded our piece of paper exactly in half, this would lie exactly on top of this. The ordered pairs are just switched. Here's 0, 3, 3, 0, 1, 4, 4, 1. The ordered pairs are just switched. In other words, the x and the y are just switched. So let's talk about confirming or proving or verifying that two functions are in fact an inverse of one another. What it means is that when you compose them together, both ways you get x. So to show that two functions f and g are in fact inverses of one another, you need to show that f composed with g gives you x, and also that g composed with f of x gives you x. So let's do an example. Now, we showed before that f composed with g and g composed with f don't always give you the same thing, so you must verify both. So let's take the function f of x equals 9 minus x cubed, and g of x equals the cube root of negative x plus 9. Let's verify that they are in fact inverses of one another. So we'll start by showing that f composed with g of x does in fact give us x. So remember, f composed with g would be f of g of x. So into f, we're going to put the entire g function. F takes 9 minus your input cubed. Remember your order of operations. You're going to cube this first before subtracting. So 9 minus whatever's in the parentheses cubed. 9 minus your input cubed. Now go through your order of operations. The cube root and the cube are going to cancel. Keeping it in parentheses because I'm subtracting this entire thing, I'm going to need to distribute. Subtract the negative becomes a positive, minus 9. Then the 9 and the minus 9 will cancel, and notice we're left with x. So we were able to prove it one way. We still need to prove it the other way. So we still need to prove that g composed with f of x does give us x. G is on the outside, f is on the inside, so this is g of f of x. So into g, I'm going to put the entire f function. So remember what g did. G took the cube root of the negative of your input plus 9. The cube root of negative, whatever's in the parentheses, plus 9. So following our order of operations, we'll need to distribute this negative. And when we do, you should notice that the minus 9 and the plus 9 are going to cancel, and we're left with the cube root of x cubed, which leaves us x. So we saw that f composed with g gave us x, g composed with f gave us x. That does in fact verify that those two functions are inverses of one another. So here's a definition for you. It turns out that a function is called one-to-one if every y has only one x. We showed earlier when we talked about functions how different x values could have the same y value. Now we're expanding on that definition and we're saying a one-to-one function, there's no repeating x values and there's no repeating y values. You can check that. Remember, you check that it's a function with a vertical line test. You can check that it's one-to-one by also including what's called the horizontal line test. So if we look at these, are these one-to-one functions? Well, notice this function right here passes the horizontal line test. This is a one-to-one function. This function right here fails the vertical line test, or the horizontal line test. So this is not a one-to-one function. Same thing here. This parabola fails the horizontal line test. It's not a function. This fourth one, though, what do you notice? It does pass the horizontal line test. So does that mean it's one-to-one? Hopefully you're thinking to yourself, no, because we said one-to-one function. This fails the vertical line test. It's not a function. If it's not a function, then it certainly couldn't be a one-to-one function. So keep that in mind when you're looking at these. Now here's a fact for you. Not every function has an inverse. You can't always undo everything that you have done in a function sense. Turns out only one-to-one functions have an inverse. Well, think about that for a second. We can still undo the square, taking the square, right? X squared. What undoes squaring? Square root. But you can only take the square root of a positive number. So we start having restrictions on this. So we can restrict the domain of a non-one-to-one function to make it one-to-one so that it does have an inverse. So let's take a look at this. Let's look at x squared, the simple parabola x squared. The graph looks like this. Now remember, f and f inverse, they switch the x and y's. So this 1, 1, we would switch to be 1, 1. But this negative 1, 1 would switch to be 1, negative 1. So if you reflected this over the y equals x axis, it's not going to be a function. It's not going to pass the vertical line test. So hence the horizontal line test fails. This doesn't have an inverse. But we know that you can actually take the inverse of x squared. So if we restricted it, let's say we got rid of all of these negative x's right here, and we looked at this just for positive x, or 0. Now this passes the vertical and the horizontal line test. This is in fact a one-to-one function. So there's where our restriction comes in. We restricted the domain, which therefore made it so it has an inverse, and in turn restricts the range of the inverse function. So how do you find it? Well, remember we said the domain and the range are switched. Well, domain is your set of x's, range is your set of y's, so x and y are just switched. However, our function f of x, it's a little difficult to work with x's and f of x's, so let's go back to calling that y. So now we have our function in terms of y's and x's. Just switch x and y, switch your domain and range. Now here's where the algebra comes in. You're going to need to solve for y. Once you get y by itself, that is your inverse, so call it your inverse function. But in math, we always need to check. We need to make sure what we did actually worked. So you're going to check, and remember how you check. You do f composed with f inverse, you make sure it gets x. Then you do f inverse composed with f, and you make sure it gets x. So let's do an example. Let's find the inverse of x squared plus 1. Notice I have this restriction on x to make it a one-to-one function, so it does in fact have an inverse. It doesn't affect our process of finding the inverse, though. Step 1, instead of having this f of x, we'll call it y. Step 2, notice we just switched x and y. Step 3, we solve for we solve for y, get y by itself. Start by subtracting 1 from both sides, and then what undoes squaring something? Taking the square root. Now, when you take a square root to solve, you have to take plus or minus. But we've restricted our x's to being positive, which in turn restricts our y's when we're finding the inverse for the range, So we're just going to take the positive square root. So we don't get more than one answer, and it's not going to fail our vertical line test. Now that we have y by itself, that is in fact the inverse, so call it the inverse. The inverse is equal to the square root of x minus 1. But until we're 100% confident with these, we're going to need to check. Now on your test, I may force you to check, which means you would have to check both. So how do we check? First thing we need to do is check that f composed with f inverse gives us x. So into f, we'll put the entire inverse function we just found, which was the square root of x minus 1. So into f, we'll take our entire input, square it, and add 1. The square root and the square cancel, and we're left with x minus 1 plus 1. Those cancel, and we're left with x. So when we composed f and f inverse, we were just left with x, so that's a good start. But that's not enough. We still have to check the other way. We still have to check that f inverse composed with f gives us x. So into the inverse that we just found, we'll plug the original function f. So your inverse takes the square root of your input minus 1. So the square root of whatever's in the parentheses minus 1. There's nothing to distribute, so we can drop the parentheses, and the plus 1 and the minus 1 cancel, and we're left with the square root of x squared, which is just x. Notice when we composed both ways, we got x, so that verifies that this is in fact the inverse. So we know that the answer we got in step 4, that the inverse is equal to the square root of x minus 1, is in fact the inverse. Let's do another example. Let's find the inverse of the cube root of 3x plus 2. Well, instead of calling it f of x, again, we're going to call it y. Switching the domain and the range, we'll just switch x and y, and now we solve for y. The first thing we need to do is get rid of the cube root by cubing both sides. Once we do that, we have to subtract 2 from both sides. Divide both sides by 3, and we're left with y equals x cubed minus 2 all over 3. If we did our algebra correctly, that is in fact our inverse, so call it your inverse. Now I'm going to leave it to you on your own to check that this is in fact the inverse of this original function. Compose these two functions together both ways and make sure that you get x. Until next time, have a great day.